Before we get into the actual physics of ideal gases, we must partake in a slight chemistry interlude to define the mole. In physics, we use moles as the SI unit for an amount of a substance. But just how much is this? Well, 1 mole of any substance will always contain an Avogadro's constant number of particles, or approximately 6.02 times 10 to the power of 23 particles. Therefore, for a substance with capital N particles, the number of moles lowercase n will be given by n equals n on Na. Additionally, we also have that the number of moles is n equals lowercase m on capital M, where capital M is the molar mass of the substance, or the mass of 1 mole. Note that this second formula is not in your data booklet, and it will need to be used in many questions, so you'll have to memorize it. Here's a brief question to make this clear. What mass, in grams, of gold has the same number of particles as 4 grams of oxygen? Go ahead, give this a try. Oxygen has a molar mass of 16 grams per mole, so 4 grams would imply 0.25 moles. Hence, we must have 0.25 moles of gold as well, which corresponds to around 49.2 grams. Now we can move on to the gas laws themselves. We define pressure as force per unit area. This unit, the Newton per square meter, is known as the Pascal. In a more physical sense, when molecules collide with the walls of the container, by Newton's third and second laws, they will exert a force on the wall equal and opposite to that which is exerted on them. This can be proved mathematically by considering the momentum of the molecule, as is shown in the background. Considering that this happens with many molecules, it turns out that a force or pressure is exerted on the wall. Before we cover the formulas for gas laws, we must first define the concept of an ideal gas, which is what we will be assuming during calculations. There are 6 postulates for ideal gases, all of which must be memorized as they can easily appear in multiple choice questions. Our first postulate is that the molecules are point particles with negligible volumes. The second is that these molecules obey the laws of classical mechanics. The third is that intermolecular forces between particles are negligible except during collisions. The fourth is that the time of collisions is negligible compared to the time between collisions. The fifth is that collisions between particles and walls are all elastic. And the final postulate, our sixth, is that molecules all have a range of speeds and move randomly. Real gases, of course, do not exhibit all of these properties. However, they will most closely exhibit them at low densities and high temperatures. At low densities, particles are further apart, so intermolecular forces become negligible. Additionally, at high temperatures, the average kinetic energy of the particles is very high, meaning that the movement is more erratic, which also leads to negligible intermolecular forces. Now, there are multiple formulas which relate the quantities pressure, volume, temperature, and amount. Before we derive the equation which relates all 4, however, we must consider 3 laws which were determined experimentally. The first is Boyle's law, which states that PV is constant, or that pressure is inversely proportional to volume. The second is Charles's law, which states that V over T is constant, or volume is proportional to temperature. The third is Gay-Lussac's law, which states that P over T is constant, or that pressure is proportional to temperature. If we combine all 3 of these, we derive that PV on T is constant. Experimentally, it can be proven that this quantity is proportional to the number of moles N. If this is measured for different quantities, it can be proven that the constant of proportionality is the gas constant, R, which has a numerical value of approximately 8.31 joules per Kelvin per mole. Hence, we derive that PV equals nRT. A constant which you came across in B.1 is the Boltzmann constant. This is related mathematically to the gas constant as Kb equals R over Na. Hence, we can rewrite the ideal gas equation as PV equals N kBT. For those interested, I will now provide a derivation of the ideal gas equation using statistical mechanics and the assumptions stated before. This is entirely optional, however, though I do recommend you to watch it and follow along as an exercise. As we showed earlier, The change in momentum for each collision between a particle and a wall is 2 mvx, or I have abbreviated v cosine theta as vx. If we assume elastic collisions, the particle will rebound and hit the other wall. Also, if we assume that this particle is in a box of length L, so volume L cubed, we derive that the time between collisions is 2L on Vx. Hence, the force which a particle exerts on the wall is given by mvx squared over L. The total pressure, then, for capital N particles is the total force divided by the area, which can be simplified to m over v times the sum of the squared x velocities. But the sum of this is equivalent to the mean square speed divided by the number of particles. Hence, we derive that p equals nm over v times the mean square x velocity. Now, since the movement is random under assumption 6, the mean square velocities are the same in each component, x, y, and z. As such, the mean square x velocity is 1/3 of the mean square velocity. Substituting, we derive PV equals 1/3 nm times the mean square velocity. Additionally, we know that the mean translational kinetic energy of each particle is 1/2 m times the mean square velocity. Total kinetic energy, then, is n times this quantity. If we substitute this into our earlier equation for PV, we find that PV equals 2/3 ek. We also know from B.1 that for a monatomic ideal gas particle, the mean kinetic energy is given by 3/2 kBt. Since the mean kinetic energy times the number of particles is the kinetic energy, we finally derive PV equals n kBt. Now we'll do a practice problem. A hot air balloon is filled with helium, which has molar mass 4 grams per mole, where the temperature is 27 degrees Celsius and the pressure 1.01 times 10 to the power of 5 pascals. At ground level, the volume of the balloon is 1.5 meters cubed. Firstly, find the number of moles in the balloon. Secondly, show that the square root of the mean square speed can be given by the square root of RT over capital M. Hence, calculate this root mean square speed at ground levels. Lastly, the balloon rises to a new altitude, where pressure is 2.5 times 10 to the power of 4 pascals and the temperature is minus 33 degrees Celsius. Find the new volume of the balloon. Please, give this a try before seeing my solution. For the first part, we must convert to SI units, so the temperature is converted to 300 Kelvin. Solving for n, we find n equals PV on RT, which evaluates to approximately 60.8 moles. For the second part, we know that the mean kinetic energy is 3/2 kBt, but it is also 1/2 m times the mean square speed. Rearranging and taking the square root of both sides, we see that the root mean square speed is the square root of 3 kBt over m. But kb over m is equal to r over m and a, but m and a is equivalent to the number of particles times the molar mass. For one particle, this is equivalent to the molar mass capital M. Hence, the result is proved. Numerically, using 4 times 10 to the minus 3 kilograms per mole, we get approximately 1,370 meters per second. Lastly, for the final part, the number of moles is fixed, so we use PV on T as constant. If we plug in our numbers and solve, we get approximately 4.85 meters cubed. Finally, there are just 2 simple equations which we must derive. The first is one which we nearly got to in our derivation of the ideal gas law. If you remember, we showed that P equals Nm on V times the mean square speed. But we know that Nm is just the total mass of the gas. Hence, we derive that P equals rho times the mean square speed, where rho is the density, mass per unit volume. Additionally, we must consider the internal energy of the gas. For an ideal gas, the internal energy is only the sum of the kinetic energies of the particles, as intermolecular forces are negligible, so there is no potential energy. Using the previous result, Ek bar equals 3/2 kBt, it follows that U equals 3/2 n kBt. By the ideal gas equation, this is equivalent to 3/2 PV. Okay, now we have a final practice problem. A balloon of volume V0 contains n moles of helium at temperature T0 and pressure P0. Firstly, derive an expression for density ρ0 of the helium in terms of the moles lowercase n the molar mass capital M and the volume V0. Secondly, show that rho equals Pm over RT. Thirdly, the balloon rises so that the pressure halves and temperature decreases by a factor of 5 on 6. Find the new density ρ1 in terms of ρ0. Lastly, use that result to show that the ratios of the root mean square speeds can be written as the square root of 5p1 on 3p0. For the first part, the total mass of helium is N capital M. Hence, ρ0 is Nm on V0. For part B, we must use the ideal gas equation to find density. PV equals M on M RT, hence Pm on RT equals M on V equals rho QED. For part C, we substitute our ratios into this expression. So P1 equals P0 on 2 and T1 equals 5T0 on 6. Hence, we find that ρ1 is 6 over 10 or 3/5 times ρ0. For part D, I'll actually leave this as an exercise to you, the viewer. With the answers to part B and C, you should be able to answer this easily, and I do genuinely want you to try it rather than just watching me passively. Thank you for watching, and have a good day.